Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video, we're going to be talking about design of compression members according to Canadian Standard 08614. So when I'm talking about compression members, we're talking about columns or members in trusses that take compression or members in diaphragms that happen to take compression. There's lots of ways that we can run into this, but a compression member is an element that is going to take compression parallel to grain. We're going to talk later about how to design for compression perpendicular to grain, but those cases are mostly for bearing locations where one piece is sitting on another. So the primary use of that piece is probably not for compression perpendicular, but we have to design for compression perpendicular just as a function of designing a beam or something like that. What we're talking about today is members that are loaded like this, compression parallel to grain, columns, etc. And of course, the things that we have to worry about when we're designing compression parallel to grain, one is crushing. So if I take this piece and press it hard enough, eventually it's going to lose strength and crush. And the other piece, of course, that we need to consider is buckling, because when I have more slender pieces of wood, then I press on them, eventually they are going to buckle. I'm trying not to break this in my face. Okay, like if I had this ruler. Ooh, a green ruler was a really bad choice. Okay, so we're going to learn this for both lumber and glulam. If I shorten it, I might write compression parallel with the two little lines, just meaning parallel. And the nice thing about designing for compression parallel is that for lumber and glulam, the process is almost identical with a few caveats that we need to consider. So if I look at the lumber equation for compression parallel, which comes from clause 6.5.6.2, we have a PR, which is a compression resistance, equals phi. We have, again, a stress times an area. So that gives you some indication that that represents kind of a crushing stress, that piece of the equation. Okay, then we have a KZC, which is a size effect factor, and we have a KC. And this KC is the piece that is going to account for buckling. Okay, so the rest of the equation is kind of a compression crushing strength, and Kc is going to reduce that strength according to the slenderness of the element to account for the potential that it will buckle. And as I said, Kzc is a size effect factor, which we've looked into before, and all those other factors have not gone away because they are still contained in Fc. Capital FC, which contains the duration factor, system effect factor, treatment factor, and service condition factor. Okay, for glulam, it's almost identical. So you see we have PR, phi, FC, again, capital FC, which contains the modification factors. A is a cross-sectional area. Then we have a KZC, again, G, the G being glulam, KZCG. And then we have KC, which is again our slenderness effect factor. Now the big difference between these two is actually in how we deal with the size effect. And you can imagine that size effect for lumber and size effect for glulam are different because lumber is made of a single piece like this, whereas glulam is an engineered wood product made of multiple pieces all glued together. So for lumber, we have this equation, KZC equals 6.3 dl to the power of negative 0.13, and this has to be less than or equal to 1.3. And when I say it has to be less than or equal to 1.3, I mean in this case, the 1.3 is a cap. So if we have something that comes out greater than 1.3, we just cap that value of KZC at 1.3. Okay, now this is a weird equation. It has an exponent that's a negative and that's a fractional exponent. So it's kind of like, it's not a square root, but it's some kind of root. And this is a good indication to us that this equation is determined empirically. So there's a bunch of test data that someone has done for size effect for compression and drawn a fit line, and that fit line is some kind of power fit, and this is basically the fit parameter that they got. So that's why it doesn't seem like a mechanically derived equation, right? But that's fine. Sometimes we have to do that. We need to use empirical data. So in this case, So in this equation, the D is the cross-sectional dimension in the direction of buckling in millimeters, and L is the length associated with the member dimension in millimeters. This is a bit of a difficult concept to get of my ruler, which appears white because it's like going through my face because of the green screen behind me. But here, if I have my ruler, I have two ways that this ruler can buckle, right? I have a long dimension and I have a short dimension of this ruler, right? The cross section, let's pretend that this is a rectangular cross section. So I have a thickness and I have a width. So this would be my depth, this would be my thickness. But D now is either one of these, depending on which direction of buckling we're trying to calculate the strength for. And for lumber, we have to do both. So we're going to do this equation twice. When I do this kind of buckling, which is the weak axis buckling, right? I'm going to use the weak dimension. So I'm going to use the thickness for D. Okay, so D here will be, you know, in this case, it's a few millimeters, but for a piece of wood, it's whatever it is. Okay, so again, if I'm buckling in the weak axis, if I'm trying to calculate my strength, including buckling in the weak axis, then I'm going to use this thin dimension. The buckling is going this way, and the dimension, this thickness dimension, also goes this way. That's how I remember it. If I do buckling in the other direction, which I can't actually do with this ruler because obviously it's too stiff to buckle in the other direction, but if this buckled like this, then I'm going to, then the buckling is in this direction, and the dimension that I'm going to use is this long dimension. It's the dimension in the same direction as the way that this buckles. Okay, so that makes sense because I'm trying to figure out the way it buckles that way, and this dimension is going to be the important one for figuring out that that buckling. So it's a size effect related to the direction of buckling, okay, which is very tricky. Now, length here is a total length associated with the member dimension, and that member dimension is D. So if I'm saying that I have buckling in this direction, then it's this total length, bottom to top, that I'm going to use for buckling in that direction, if that's the buckling mode I'm talking about. We're going to talk about those buckling modes in a second when we calculate effective length, but this is not the effective length, it is the length of buckling. So if I had this restrained in the center, then the buckling will go a bit different. Like, so for example, if I had this restrained at the bottom and at the top and also at the center, then obviously this thing is not going to buckle from bottom to top because it can't move here. So then my effective length for buckling in this weak axis direction would just be this length here. Okay, it's not the effective length, which is K times that, which we're going to talk about if you're reviewing this video, but it's actually just this length here. So it's the length associated with buckling with the member dimension that we're using. These things will become more clear when you do some examples. Okay, for glulam, the size effect is a bit different. Okay, so for glulam on the right, the size effect factor is based on total volume. So it doesn't matter which way of buckling we're talking about. If I have a glulam member, this is my glulam member, it's just the total volume of this member. So I'm going to go from end to end, and then the width times the thickness, and that will give me my total volume. Now, a big thing here that we need to remember is that since these are empirically derived equations, which you can tell that this one is too, it also has a kind of funny exponent and a coefficient in front of it, like 0.68. On top of it being empirically derived, that also means that the units are going to be important. Whenever we have exponents that are funny roots like that, then we can tell that the unit that we put in for our variable is going to be important. Because if I do square root of 100 versus square root of 0.1, it's going to be different. So in the right side for glulam, we have to make sure that the Z is in units of meter cubed. If you don't use meter cubed, you're going to get the wrong value. Okay, just like on the left for lumber, you must use dimensions of millimeters for D and L. And if you don't, then you're going to get the wrong number. Okay, so make sure that you watch for units in these equations. So for the glulam size effect factor, it has the same kind of thing where the size effect is capped off at 1.0. So that means if you get something out of that equation that's greater than 1.0, you just say, nope, we're capping it off at 1. And then you just use KZG equal to 1. Okay, so one of the consequences of these is that for lumber, since we have a different size effect factor in each direction, And since our Kc, as we will see, the factor that accounts for buckling, the slenderness factor that accounts for buckling, also changes based on which direction we go, we need to actually calculate the strength in two directions all the time for lumber. So we need to look at my lumber member. I need to look at it bending in this way, buckling in this way, and for buckling in this way all the time. Even if it looks like one is going to govern, it says specifically in the standard that you must check buckling in both directions. So in the standard in clause 6.5.6.2.1, it says specifically that you need to check it in both directions. And the reason for that is because when I have a size effect factor that gets bigger, I have typically a slenderness factor that gets smaller, and vice versa. And so it's not clear from the equation, it's not the case that all the time one is going to govern over the other. So I can't just say the one that has the higher slenderness, for example, is going to be the one to give me the smallest Kc, which is going to give me the smallest strength, which is what we'll see in a second is what we're going to do for glulam. So for glulam, we only need to check this equation once, and basically what we'll do is we'll figure out which direction gives us the lowest Kc, right? Kc is our reduction factor to account for slenderness, and the Kc that's going to be the lowest is going to be the one with the slenderness that is the highest. So we're going to calculate the slenderness, see which one is higher. A more slender member is going to be more likely to buckle, and then that is going to give us our lowest value of Kc, and that's what we're going to use in the equation, just using the size effect factor above. So this is the main difference between compression parallel in lumber versus glulam. Is in lumber I have to check it twice. In glulam I only have to check one direction. In lumber I have one calculation for size effect, and in glulam I have a slightly different one. Okay, now what about the things that are the same between both lumber and glulam? So in both lumber and glulam, the phi factor for compression is the same. It's 0.8, which is different than what we had for tension. And the FC, the large FC, which represents our material strength, is also the same. So we get FC, although from different tables. So small FC for lumber is going to come from tables 6.3.1 A through D, like we saw before. And FC for glulam is going to come from table 7.3. The service condition factor KSC also comes from different tables for both, but anyway, this equation is the same. And we saw how to get KSC before. We go to the tables in the standard in chapter 6 and chapter 7 that basically lay out all of these factors for us. We talked about how to do size effect. Sorry, not size effect. We talked about how to do treatment effect previously. We talked about system factor, and we talked about duration factor. Okay, so how do we calculate this slenderness factor, which is the part of the equation that accounts for buckling? Okay, so that slenderness factor is going to depend primarily on the geometry of the member and how slender it is. How slender something is how likely it's going to buckle. So something like this is quite slender in one direction and easy to buckle, this ruler. And in the other direction, as we saw, it's not very likely to buckle. It's very, very stiff in that direction. So it has a different slenderness for buckling in this direction than it has in this direction. And if I want to calculate the slenderness for this piece, what I'll do, so for width versus depth, the way that I'm defining is width is the thin direction and depth is the large direction. So if I had it for 2x4, then I'm defining width like this and depth like this. And the width is associated for buckling in the weak axis, and the depth is associated with buckling in the strong axis. So you can imagine that weak axis buckling is for this ruler this way, and strong axis buckling for this ruler is this way, which it can't actually buckle in this direction, right? For this particular one. So that's how we calculate that. And you'll notice that it doesn't just say length in that equation. It says effective length, which is our L sub E. L sub E. So some places in these equations it says L, Like, for example, when we're calculating our size effect factor for lumber on the left, we use L, not LE. But in this equation for slenderness, we are using LE, which is an effective length. And that effective length depends on both the on both the boundary conditions of the member and on any other restraints there are associated with the member. We're going to see what that means in detail. Now, in the standard, it just says CC. It has two equations for CC. One, it says CC effective length associated with width divided by member width, and then it says CC again, effective length associated with depth divided by member depth. And I added this little subscript weak and subscript strong, and that I just like to do in order for me to be able to keep a bit track of it. Now, it doesn't mean that the strong axis slenderness is going to be necessarily less than the weak axis slenderness. I'm just keeping track literally about which way is weak for the cross section and which way is strong for the cross section. And you might see that that helps you keep track as well. So to clarify this a little bit more, let's draw actually a cross section of a piece of wood. Okay, so here is piece. I'm drawing the X through it. So this is a piece of lumber. I'm looking at the cross section, looking at it like this. And I'm saying that this here is the depth. And this here dimension is the width. Okay, and just like we talk about for steel design, we can have bending in two different dimensions, right? I could call this Y. If this was a steel beam, that would be Y. This one would be X. Okay, so if I'm talking about which way this buckles, okay, buckling in this direction would be, I would call that buckling in the strong axis direction. And then buckling in this direction, I would call that buckling in the weak axis direction. Okay, so to show using the ruler again, here I have like this. So when I say buckling in the weak axis direction, I mean buckling like this. Okay, so if I'm looking at that cross section and I see that it's buckling like in this direction, that's buckling in the weak axis direction. Okay, so that is my CC weak, the slenderness I calculate for that. And buckling in the strong axis direction would be buckling like this. Okay, if I were to press on it and it buckled in this direction, then that would be buckling in the strong axis direction. So for buckling in the weak axis direction, I use the width. Buckling in the weak axis direction, it's hard to show. Buckling in the weak axis direction, I'm going to use the width, which would be like the thickness of this cross section. Buckling for the strong axis direction, I would use the depth, which is this long dimension here. Okay, I hope that clarifies. Okay, there is one additional requirement, and this is a hard requirement. This is not a cap, is that the CC, the slenderness, for both directions, neither of them can be greater than 50. So if I do a calculation and it gives me CC greater than 50, I don't say, okay, it's greater, so I'm going to cap it at 50. I have to change my design to make sure that the slenderness is less than 50. So I can do that by increasing the cross-section, because increasing the cross-section would increase the denominator here, right? So if I increase the member width, that's going to make CC go down. So I could do that. Or, I could change, the other thing that I can change in this equation is the effective length. And I can do that, like maybe the total length is, I can't change, but I can change the effective length by adding a support somewhere in the middle, or by changing the boundary conditions to make it bend differently. So let's dive in a bit more about what this effective length actually is, how I calculate it. So that effective length, as I mentioned before, depends A, on the boundary conditions. So that means how the member is held at the end. Now in timber, the boundary conditions are almost always pinned, which means the member is allowed to rotate in the end. And that's because it's very difficult to design a moment connection at the end of a timber member. So not a lot of opportunity to change boundary conditions, but what we can do is add restraints. So let's look at an example, and I'm going to draw a example right here. Okay, so here I've drawn a timber member in the vertical direction, and let's say I want to find out what is the resistance of this member to compression in the vertical direction. And I'm saying right here, oops. And on eraser, I'm saying right here that this here is a pin support. So it does not restrain the rotation, it only restrains the translation. So it can't move left or right and up and down, but it can rotate. Okay, so stuff that you've seen in structural analysis before. Okay, so now I can calculate lengths associated with buckling, and then I can figure out the KE. So there's two different things here. Okay, so now in the strong axis direction of this piece of wood, if it buckles, you know, in the strong axis direction being in this direction, so in the picture, it's kind of in the out of plane direction. So you can imagine it buckling in that direction. I have a certain effective length, not effective length, sorry, just length. This length here, this is my length associated with strong axis buckling. Now, if I'm talking about weak axis buckling, I'm assuming that these horizontal members here are not free. They're attached to something else. So they are restraining the movement of that piece. So if I have my member in the middle like this, and I have a piece coming here and a piece coming here, and they're preventing that member from moving horizontally at that location. So that means that if I put a compression load on this, it can't buckle in the normal way, right? Like end to end, because that requires the middle to move. Okay, so it can only buckle between the end support and the restraint. So now I've shortened my length for buckling. And you know, because you've probably looked at Euler buckling before, like simple elastic buckling, that as I reduce the length for buckling, the buckling load goes way up. So that will make a big effect on my total strength that I'm calculating. So if I'm looking for my length associated with weak axis buckling, here I have two. This is my L for weak axis buckling. And this is another L here for weak axis buckling. These might be different. This could be L for weak axis buckling 1, and this could be L for weak axis buckling 2. And if that was the case, then we're going to have to check two different effective lengths. So again, just to make sure that I'm clear, this here, these are not effective lengths. These are just buckling lengths. Okay, when I want to calculate effective lengths, I also have to take into account what the boundary conditions are like. So how do we do that? We're going to look at this same case for the strong axis buckling and the weak axis buckling. So in this case, for strong axis, okay, if I just make it more of a schematic than a 3D drawing, I have something that looks like this. Okay, I'm applying a load, right? Like I'm moving that restraint down. So obviously, you know that those kind of pins can't move down, so we have to say that this is some kind of thing that can roll downwards. But anyway, so basically I'm applying a vertical load to this, but these ends are not allowed to translate left and right. The top can move down, but it can't translate left and right. And then so we're going to get a buckling shape that's going to look something like this. That's how it's going to buckle. Okay, and then this length here is our L strong from above. Okay, now if I want to calculate my effective length for this, then I have to consider the boundary condition. So I have now equation LE equals KE times L. In this case, since I have simple buckling, pin-pin buckling, my KE happens to be 1.0. So now I'm going to have 1.0 times L strong, and that's going to be my LE. It just so happens that in this case, LE equals that L. Okay. Now, if I want to look at a whole bunch of cases for this, I can go to the standard, and in the standard, we have effective length factors, KE, for all different types of boundary conditions. So you see the one that we were just looking at is the third one here, which is held in position at both ends, but not restrained against rotation. So this is a pin-pin situation, and you can see the KE equals 1.0. So we have lots of other conditions here. If I just had a cantilever where the top is allowed to move left and right, like it's just held at the base fixed, and as I push here, it can move left and right, then you can see that the buckling is instead going, the effective length factor to account for buckling is going to be 2.0. Okay, so let's look at our weak axis case for this particular example. So if I do weak axis, I still have pin at the top. I still have pin at the bottom, but now I have a support at the center that's going to keep it from moving laterally at the center. So the way that this is going to buckle is something like this. So my length, my weak length here, L weak, is like this. And then I have to figure out what is my KE factor for that. And to do that, okay, LE equals KE times L again. To do that, I can look at that table again, and I can look at the way that this bends, that this buckles. So since this buckles in a shape like this, which is like a half of a, like kind of half of a sine, that's not necessarily exactly what the shape is, but just how I'm describing it, it's like this kind of curve, then I can go back to the thing here and find which one has a curve that looks like that. And again, it's the same one here, which is 1.0 for KE. So this one is also going to be 1.0 this time times L weak. So now I have my L, which is what I'm going to use in my size effect factor, and I have my LE, which is what I use in my slenderness. So if I go back, if we recall way back at the beginning when we talked about size effect for lumber, on the left we have KZC equals 6.3 times DL in brackets. That L is associated with member direction. For the case that we're just looking at, if I'm talking about strong axis buckling, my D is going to be the strong axis dimension, the large dimension, times the full length of that. Okay, so if I come down here, my D is going to be my strong axis. So it's the long dimension, this one here, right? And my length is going to be the total buckling length, because that is the strong length. If I'm talking about repeating that equation, which I need to do, I need to calculate it in the weak axis direction as well. Now my D is going to be the short direction of the cross section and the length that it's going to buckle over. And for this example, for this example, the length that it buckles over is only half the length because it's restrained in the center. So now my L is going to be L weak, which is half. So my D is going to be the short axis direction, and my L is going to be the L weak as shown here. So that's how I use that particular equation. Okay, which we needed to return to. And as I mentioned, the L that we use for this equation, the slenderness factor, is the effective length, which is the KE times that L. And that's how I determine my slenderness. Okay, now let's look at just a few more difficult examples of how to find that slenderness, effective length factor, sorry. So we're going to look at something that's more complicated. These will come up quite rarely because usually for wood, we're mostly talking about simply supported end conditions, which means that KE is usually 1. But sometimes it's not. So if I did have some sort of case where I had a continuous member, for example, or something like that, where the end conditions were actually effectively fixed, then my buckling is going to look like this, right? And if I go back to my table and look at it, then you can see that that is the same as the first one here, which is a KE of 0.65. So here I say KE equals 0.65. Okay, what about if I had a case where I had a fixed condition on the top so it can't rotate and a pinned condition on the bottom? Then this thing is going to deform something like this. And if I go back to my table, then you can see that that's equivalent to this one here. It's the upside down of this one right here, the 0.8. So I'm going to say KE equals 0.8 for this one. Now, what if I have a case that's even more complicated where I have a fixed condition at the top, and I'm going to make it a bit longer so it's easier to draw, and I have a pin at the bottom, and I have an intermediate support, okay? And so now it's not exactly like one of the ones in the table, but I can intuit how this thing is going to deform, something like this. Then I'm going to have a different K for the top as I have for the bottom. And basically I'm going to look at that deflected shape of buckling, and I can see the one at the top is kind of straight at the top because it can't rotate, and it bends out and buckles in the middle. So if I go back to the table, get my actual pointer, oops, then it's going to look basically the same as this one, right? So it's fixed upside down again. So this one was fixed at the top, and in the center it was allowed to rotate. So for the top of that one, it's going to be KE equals 0.8. At the bottom, we have basically just a simple bend shape, one of these again, right? And for that one, we know before KE equals 1.0. So now if I'm designing this particular one on the very right, then I'm going to have to do two different calculations, one for buckling of the top section in the weak axis, if that's the weak axis buckling, and one for the bottom section if it's weak axis. Now, if they're both the same length, if those two are the same length, the top and bottom, then obviously it's going to be the KE of 1.0 that's going to govern, because it's going to give me a larger slenderness. So slenderness is dependent on length. Effective length, KE times L being greater, is going to give me a bigger slenderness. So I don't have to check both of them if I can tell. Basically, I should check which one has the greater slenderness. Yeah. Okay. So what do? We've calculated our effective lengths. We've broken it down into strong axis buckling and weak axis buckling, and I found the effective lengths for both. If I'm talking about, and I found the slenderness for both. Okay. Now what do? So returning all the way back to finding KC, which is where we started, and why we needed to find the slenderness, and therefore why we need to calculate the effective lengths. So I calculate my effective lengths, I calculate my slenderness values, CC strong and CC weak, and then what do I do with it? For KC, I have the equation for KC, which I'm going to put out in a minute, which is functionally identical for lumber and glulam. If I'm talking about lumber, as I mentioned before, we have to check both directions. So I'm going to use both CC factors in that KC equation to get two different KC values. Okay, and I'm going to use both of those in the equation for compression parallel strength to get two different compression parallel strength values and then take the minimum. The reason is because the size effect factor for those two is going to be different for those two directions. So I need to check both. For glulam, I'm going to get my slenderness for both directions, CC strong and CC weak. I'm going to find whichever of them is greater, which is a bigger slenderness, which means more likely to buckle. And then I'm going to use whichever one of those is greater to calculate what would be the minimum KC value. And the KC equation looks like this. Okay, so here I have KC. This is the equation for KC. See, it's just a bit involved, but not so bad. I have a 1.0 plus my strength, FC, times my size effect factor, which we saw before. It's the same size effect factor that was in the equation for PR at the very beginning. I have my slenderness CC in whichever direction I'm calculating. So that's CC strong or CC weak. We do one or the other, right? For lumber, we're gonna repeat this calculation for one CC, then do it again for the other CC, strong and weak. Then I have a factor of 35 on the bottom. E05 is my 5th percentile Young's modulus. Which we're going to talk about in a second. KSE is a service condition factor associated with stiffness. So that comes from table 6.4.2 or 7.4.2 for glulam. KT is my regular treatment factor. And do not forget that the whole thing here is to the power of -1. So I calculate everything inside the brackets and then I find the inverse of that, and that gives me my KC. So larger CC means a lower KC. Okay, so where do I get my 5th percentile Young's modulus? For lumber, I get it in the tables directly in 6.3.1 A through D. For example, we see here we have modulus of elasticity. We talked about before that we have 2 different modulus of elasticity values for each stiffness species grade combination. E05 is a 5th percentile strength, which means it's an effective lower bound on the stiffness. Why do we use that in this equation? Because in this equation, we're using the elasticity in a strength calculation. So we don't want to use the mean value. The mean value we use for things that are like serviceability conditions. If I want to calculate deflections, I just want to know what is the actual deflection, because it's not going to hurt anybody if the deflection is a little bit bigger or a little bit smaller. But for E05, since I need this E value to calculate the buckling strength, then I need to make sure that I use a 5th percentile, which means I want 95% of all values to be greater than that, because now it's a safety issue. Okay, for glulam, then E05 is actually an equation. We use 0.87 times the E from table 7.3. So in table 7.3, basically we have an E value down here, modulus of elasticity, and this is the mean value for modulus of elasticity, so we can't use that. It's not conservative enough. So in the equation, in the calculation for KC here, it says specifically that in order to calculate E05, I can just use 87% of the E, and that gives me an approximation of the 5th percentile. Okay, so now that I have all of those things, I've calculated, to review the process, I have calculated my length for buckling in both directions. Then I calculated my effective length for buckling in both directions, taking into account the boundary conditions and the supports, going to that table that I showed you in the back of the standard in the appendix. And then once I have that effective length, I can calculate the slenderness ratio. I have to make sure that that slenderness ratio is less than 50. So if it's not, I have to change my design. Then once I have my slenderness ratio for both directions, strong and weak, I come to this KC equation here, and I sub in both slendernesses for lumber to get 2 different KCs. For glulam, I just use whichever CC is greater, and I plug that into this equation to get my minimum KC. Then once I have all of those things, I come all the way back to my initial equation. I'm going to plug in FC, which applies all of my modification factors, A, which is my cross-sectional area, KZC, which is from these equations, and KC for lumber in both directions, and for glulam, just the minimum one, and then I'm going to come up with my PR. So for lumber, I have two KCs. For the KC, I have to use the appropriate size effect factor depending on the direction. Remember that D here is the dimension in the direction of buckling, and L is not the effective length, but the length for buckling in that direction. And so I'm going to do this calculation for PR twice. And then after I do that, whichever one is the minimum is going to be my design compression strength.